We are now beginning chapter 9, which is about transformations. For this lesson, we will be doing the first three sections of chapter 9. Each one of them deals with a different transformation. The first will deal with reflections, 9:1. The second will deal with translations, which is 9:2. The third with rotations. You'll notice with all three of these transformations, the original, which is called the pre-image, and the second, the copy, which is called the image, they're the same size and shape. That is to say, they're congruent. It's true also for rotations. Despite the fact that it has been turned, the angles are still the same, the side lengths are still the same, and it's also true of reflections. These are therefore called congruence transformations, or another big word, isometries. The lone transformation that's not is a dilation. You'll notice that the original, the pre-image, gets smaller, and the image is smaller than the pre-image, and therefore the dilation is not a congruence transformation. I should mention also that sometimes you start with a small pre-image and the image is larger. You've seen these before as slides, turns, and flips. We're gonna use the more technical term. Okay, let's begin with reflections. A lot of information on this page. A few things I want to point out. When you have a reflection, there's only one thing that matters. That is the line of reflection. If you think of reflections as something that happens in a mirror, the line of reflection is the mirror. The way we get from an old point to a new point is we draw a segment perpendicular to the line of reflection, and then we go that same distance again. This again is the pre-image. This is the image. You'll notice this little mark here, we call that prime. So B is the original point, and B is the pre-image, B prime would be the image. Okay, linear reflection is pretty simple, but point reflection is a little bit more confusing. To get from point B, the pre-image, to B prime, all that's done is you go directly to the point of reflection and then repeat the process. Go that same distance again. And so from A to M, we go that same distance again. It takes us to A prime. You'll probably notice that a point reflection looks a lot like a 180-degree rotation. And they really are identical transformations, actually. Typically, when we do reflections, we do them in the coordinate plane. And so we're going to take one point, and I'm going to reflect it over several lines, and one point in the coordinate plane. These are really the only ones we're very interested in. We're only doing this exercise with one point. It's very similar when we do it with polygons. We just choose each vertex and repeat the process for each vertex. Okay, so we'll start flipping over the x-axis. To go to the x-axis, I go up 2. To reflect it, I'm going to go up 2 more. And I'm going to call this little a. I know we typically name points with capital letters, but I want to keep my reflection straight. So you'll notice that the only thing that changes about the coordinates, is the sign of the y coordinate. When I reflect over the y-axis, left 3 more, call this point B, you'll notice the only thing that changed is the sign of the x-coordinate, which seems a little bit backwards. And I'm going to go ahead and flip over the line y equals x. It's our other line. I'm going to make a perpendicular line and then go that far again to get to my new point. And I hope you'll trust me that this point is -2, +3. I hope you can see that all that happened is the x and the y trade places. And then finally, let's flip over the origin. I'll remind you to flip over a point. You go to that point, so I'm going to go left 3 up 2, left 3 up 2, and that gives me the new coordinates. -3, +2. Okay, so when we flip over the origin, what happens is both signs change, but the x and the y stay in the same place. Okay, we typically represent transformations this way. We start with the point xy. Where does it go? It depends on what we do to it. When we flipped it over the x-axis, the only thing that changed was the y-coordinate switched from positive to negative or negative to positive. Over the y-axis, the only thing that changes is the x. So if we start with a positive x, we end up with a negative x, and vice versa. When we flip over the origin, the x and the y both become negative. So both signs change. And then finally, if we flip over the line y equals x, the x and the y trade places. Reflections, we learned about symmetry, which I'm sure you learned about this in elementary school. Lines of symmetry are lines over which you can fold an object and it appears to not change. Or rather, it's mapped onto itself. So we have 5 sides, and surprisingly, or not surprisingly, we have 5 lines of symmetry. The other thing we need to talk about is point symmetry, and that's something that's either a yes-no. You can't have more than one point of symmetry. It's just yes or no. The way you test that is you start with an original point, and you reflect it about the point in the middle. So if I go there, and I go that far again, it's going to take me below. Okay, so this does not actually have, if I were to reflect every point, this object does not have point symmetry. And typically, polygons that have an odd number of sides do not have point symmetry. Rather, it's reserved for even-sided polygons. Okay, translations. This one's the easiest one. So we'll just start off with an example. Remember, translation is a slide. We want to move from the red pre-image to the blue image. All we have to do is keep up with how many we go to the right or left, how many we go up or down. So I'm going to count off. I know it's difficult to see, but it's 1, 2, 3, 4, 5, 6, 7 to the right, and 1, 2, 3 steps down. You'll notice that all I looked at was one point in particular. There's no point considering the whole object, but 7 right and 3 down. And let me show you real quick how we write this. Just like we do with reflections. We start at xy. Where does it get mapped to? Well, what did I do to the x coordinate? I moved it 7 to the right. So the new one's going to be x plus 7. What happened to the y coordinate? I moved it 3 down. That's like taking away 3 from the y. And that's how you write a translation. Okay, so if I'm translating D, E, F, G, 5 units to the left and 3 units down, how would I write that? 5 units to the left. Well, that means I'm subtracting 5 from my x. And if I'm going 3 units down, that's going to be y minus 3. So, to rewrite this, for D, well, D is going to become D prime. What do I do to 1? I subtract 5 from it. So that's going to be negative 4. What do I do to 2? I subtract 3 from it. That's going to become negative 1. The rest of these are just like that. Again, translations are very simple, so I'm not going to waste your time. 2 more examples. Given this translation, find the image of A. Well, A is going to get mapped to A prime. 3, it looks like I add 2. I'm moving this 2 to the right, so it's going to go 5. 7, it looks like I'm moving it 1 down, so it's going to go to 6. Find the translation that maps B to B prime. Okay, well, I'm going to start with an xy. It's going to get mapped to, what do I do to x? Well, to get from 2 to 3, I have to add 1. What do I do to y? From get to negative 4 to positive 11, I have to add 15. Again, translations are easy. All right, finally, rotations. A rotation is a turn. The important thing here is that you always have an angle of rotation and a center of rotation. For our purposes, we're going to most often use the origin in the coordinate plane. But it can be any point, really. The other thing we have is how many degrees are we turning it. And I hope you can see here what we have going is 90 degrees. Okay. Okay. To see how rotations affect coordinates, we're going to take a very simple example, 2, 1. And we're just going to follow it around the origin. So the origin is going to be our point of rotation. All right, this is the point 2, 1. Where does it go if I rotate it 90 degrees counterclockwise? And frequently we'll go counterclockwise. It goes over here to negative 1, positive 2. So you'll notice what happened is I switched the x and the y. Instead of 2, 1, now it's 1, 2. If I rotate it 90 more degrees, it's going to take me over here, which is, no sense in writing it there. I'll write it over here. -2, +1. Rotate it 90 more degrees, it goes here, which is 1, -2. If I rotate it 90 more degrees, I go back to the beginning. So the important thing to see with each step is that the x and the y always trade places for every 90 degrees. And then the other thing to keep in mind is just pay attention to which quadrant you're going to be in after the rotation. That's going to tell you which one needs to be positive and which one needs to be negative. Okay, so we've got an example here. I want to move this triangle. I'm only going to move it once in the interest of time. But we've got 3 points, 1, 1, 1, 2, and 2, 2. Okay, to get 1, 1 to the next rotate it 90 degrees, I'm going to have to change the 1 and the 1. Oh, okay, well then it's going to come 1, 1, and I'm going to be in quadrant 2. So 1, 1. And I know in quadrant 2, the first number is always negative and the second one's always positive. To move 2, 2 is similar. You switch the 2 and the 2. There's not a lot of switching involved. They're both 2. And I know, because I'm in the second quadrant, that the first one has to be negative and the y-coordinate has to be positive. Okay, 1, 2. This one's actually interesting. Instead of 1, 2, it's going to be 2, 1. Go over 2, up 1. And because I'm in this quadrant, I know that the 2 is negative and the 1 is positive. That's a 90-degree rotation. I hope you can see that. It's very clear. And actually, the Smartboard, or the Promethean board, should allow us to rotate this ourselves and see how we did. Oh, very nice. 90 degrees. You can see a 180-degree rotation, a 270-degree rotation, 360s all the way around. Very nice. Okay. Also, we talk about rotational symmetry when we talk about rotations. You'll notice a nice object like a hexagon, a regular hexagon. If I turn it 60 degrees, you can't tell the difference. I've put a little marker in the corner. But the number of times you can turn it before you get back to the beginning is called the order. So a hexagon is going to have an order of 6. I refer to these as a click. How many degrees you have to turn it before it clicks. The number of degrees you have to turn it is called the magnitude. Simply to get the magnitude, you divide 360 degrees, which is a full rotation. You divide that by the order, and that will tell you the magnitude. Okay, so for example, I have this rim here, and I want to know the order. Well, I can simply rotate this, I suppose. How many times will it click before I get the whole way around? Well, so I'm starting at 1, 1, 2, so we're up to 3, 4, 5, and if I turn it the next time, I'm the whole way around. So there are 5 clicks, if you will, and that's the order, 5. And to get the number of degrees, the magnitude, I simply divide 360 by 5, and so the magnitude is 72 degrees.